Hello guys, thank you so much for being with me in another artificial neural network tutorial video. We have reached one of the most basic topics in this field. The concept I want to introduce in this video is the computational graph. We perform steps to finally calculate the loss function. The first task was to calculate the scores. After these scores, we calculated the error of each data with a loss function and calculated the error of the whole collection by averaging. We call this part data loss. But we had another statement in the loss function that depended only on the W parameters. This sentence is the same sentence as a regularization. The sum of these two parts is the total error, the cost function actually. This resulting graph is called a computational graph. In this graph, the vertices are operations. The calculation graph shows us step by step the operation that is performed. Now, what does this help us? We proceed in the backpropagation algorithm or in the backward phase, the reverse of the forward phase and the topological order. We come from the last to the first. We go back step by step. We calculate the gradients according to the parameters step by step. The concept is a simple concept. We start with a simple example. Consider this simple function f. In this function, x is added to y and the sum is multiplied by z. You can see that in this computational graph, the vertices are operations. In the forward step, we first perform addition and then multiplication. Finally, we calculate f. But in the backward step, we want to calculate the gradients. We go step by step recursively. We represent the sum of x and y with q. We define this intermediate variable for simplicity of explanation, of course. In each node, the output depends only on the inputs of the same node. That is, it has nothing to do with the rest of the graph. And knowing these simple formulas and the differential laws, we can calculate gradients no matter how big this graph is. The goal is to calculate the differential of function f with respect to y, x, and z. We proceed to the reverse of the topological order. The first task is to start from the end of the graph and propagate the gradient along the graph. First, we calculate the differential of f with respect to itself, which is 1, because the differential of anything is 1 with respect to itself. So in the backward stage, we always start from 1. We navigate the nodes in the order of the photo backward. We have the differential of this node with respect to the output. We also have the partial differential with respect to the parameters. So with the help of the chain rule, we multiply the differential relative to the output by the partial differential to obtain the differential relative to the input. Now the point is that these inputs themselves may be the output of another node. It does not matter. Again, in the same way, we calculate the differential with respect to the next inputs. The forward stage has green numbers and the backward stage has red numbers. In the slightly larger calculation graph, I have shown both the steps in forward and backward in the slides. You can see that there is no difference. In this algorithm, we have nothing to do with the general image of the graph. Rather, in each step, we consider only the same node under investigation. Our graph may have millions of nodes. The input of each node may be the output of another node. We have to repeat the same thing at each step. This is a recursive algorithm. this example, you see a larger computational graph that works with the softmax function. This is a real example. The parameters are two-dimensional and W2 is the bias. So if we multiply W0 and X0 and W1 and X1 2 by 2 and add the result to W2, we have calculated the score. We have calculated the forward step according to the inputs and parameters. Here we have also checked the backward stage. The functions that I have put in the slide along with their differentials are the functions that are used in the nodes of this computational graph. In each node, we have the gradient relative to the output and we want the gradient relative to the input. We must multiply the output ratio differential by the local gradient. As you know, the gradient is multiplied at the switch node. We don't always want to expand that much. Parts of this computational graph sometimes represent a specific function. For example, this part of this graph represents the sigmoid function. This part, for example. This whole rectangle can be considered as a node. Here. This can be called a supernode. You can see the local gradient of this cloud node, this supernode, this hypernode in the slide. We use the same rule. Let me show you which one I mean as the hypernode, supernode. This is the sigmoid. And we can consider it as a hypernode. You can see the local gradient of this hypernode in the slide. We use the same rule of multiplying the local gradient in the output gradient to find the differential relative to the input. At the sum node, the gradient is propagated between the inputs. At the max node, the gradient is routed to the maximum input. These specific patterns exist and we can use them in calculations. In the max node, if both inputs have equal values, the gradient is transferred to one of the two inputs without any difference, and the gradient of the second input is considered 0. There is another pattern that is the accumulation of gradients in branches. In the forward stage, the output of this node has gone to two other nodes at the same green arrows. In the backward stage, we want to see how much and how the output of this node is affected by the branching nodes. This output is affected by both nodes, so we must use the plus sign. In implementing these graphs, we use ready-made packages such as TensorFlow, which is a product of Google, or PyTorch, which is a product of Facebook. Each vertex in the graph has two functions, one related to the forward stage and one related to the backward stage. Here, dz refers to the gradient of the loss function with respect to z. This computational graph gives us exactly the impression that these nodes are like Lego pieces. This view helps you to know that the implementation and architecture of artificial neural networks is very simple. When we define the gradient of a number with respect to a vector, we also have a vector for the gradient, which is equal to the value of the gradient in relation to each dimension. If the node itself is a vector, what happens? It means that both output and input are vectors. Then the gradient will be in the form of a matrix. This matrix is called the Jacobian matrix. In neural network and deep learning problems, inputs and outputs are vectors. The dimensions of this matrix may be very, very large. Because in real-world problems, the inputs and outputs can be very large, so this may occur. We can use local gradient features in the bulk calculations of this matrix. For example, in this matrix, only the elements of the main diameter can be non-zero, and the other elements are definitely zero. So there is no reason to save them, and it is enough to save the main diameter elements. You now have the ability to implement different cost functions with a few lines of code. We can calculate each of the loss functions we have seen with the same two steps forward and backward. For example, you can use L2 as regularization. In the forward step, you can calculate the loss function, and then in the backward step, you can calculate the gradients. In the last step of the forward step, you had calculated the loss function from the margins, and in the first step of the backward step, you should calculate the gradient of the loss function with respect to the margins. Now you can update W with these gradients. Have a nice time.